Good day to Dr. Olawale and Dr. Fadila. My name is Dylan Laga and I will be presenting my thesis, which is the vibration analysis on shaft fault using frequency-based technique and verification by machine learning. So first we will start with the chapter 1, which is the introduction. In this modern era, vibration analysis plays a huge part in detecting faults in any machinery by making it easier to solve the problems and doing maintenance on it. Vibration analysis can be depicted as a movement for assessing the vibration levels and frequencies of a machine, and while later using those information to separate the condition of the machine and their section. Next is the problem statement. The first problem that happen is mechanical problems in machine can cause performance drop. Second is major shaft faults are hard to detect. Third is the effectiveness of MATLAB simulating and machine learning in fault detecting. Next is the objectives. The first objective is to conduct an experiment model for normal and faulty shaft based on vibration attributes. Next is to verify the data analyzed using machine learning techniques. And lastly is to analyze the vibration signal generated by an experiment setup using frequency-based and vibration statistical analysis. Now we will go to chapter 2, which is the literature review. Here we have three types of shaft. First is the line shaft, counter shaft, and crankshaft. Here we have four types of commonly shaft faults. The first figure shows shaft failure due to fatigue. Second is shaft failure due to corrosion. Third is shaft wear. And lastly is shaft failure due to torsional overload. MATLAB simulating is a MATLAB-based graphical programming condition for illustrating, reproducing, and looking at multi-area dynamical structures. Simulating is extensively used in customized control and automated sign taking care of multi-space diversion and model-based structures. Next is the vibration analysis. According to previous studies, vibration signal is generally utilized condition for condition checking of a turning machine as one of the non-dangerous strategies. Vibration signal includes mechanical mark data about the reason for the vibration, and through its examination utilizing various strategies. Rising or creating shortcoming can be distinguished. Different apparatus are utilized, from basic instruments estimating by and large vibration to multi-channel analyzers furnished with various highlights that encourage the estimation itself. Next is the fast Fourier transform, the FFT. According to previous research, Fourier analysis of an intermittent capacity alludes to the extraction of the arrangements of sines, cosines, which when superimposed will recreate capacity. The FFT works by separating a n point time region signal into n time space hairs, each made out of a single point. Next is the time domain, which is one of the most basic and modest deficiency assurance techniques. Time domain strategies are appropriate when periodical vibration is watched and failures produce wideband frequencies dependent on intermittent driving forces. Next is the performance verification by machine learning. Machine learning alludes to a framework capacity to obtain and coordinate information through huge scope perceptions and to improve and expand itself by learning new information instead of by being customized with that information. Learning frameworks have accomplished an assortment of results, going from paltry retention to the making of whole new logical speculations, and can be possibly consistently self-improve, empowering their frameworks to turn out to be progressively productive and compelling. Next is the methodology, chapter 3. Although there are more advanced and improved sensor technology in this world, the most commonly used is the accelerometer, which can be found in the vibration lab where the research is being conducted. In many previous research, vibration analysis usually is broken down into four principles, namely time domain, frequency domain, joint domain, and model analysis. This is the flowchart for this experiment. Next is the experimental setup. The experiment will be focusing on two types of shaft condition, which is a normal straight shaft and a bended shaft. The experiment was conducted by performing a vibration analysis on the two shafts. The experiment uses four different speeds, which is 450, 900, 1350, and 1800 RPM. Before starting the experiment, the setup was run for 5 minutes to calibrate the sensors to avoid any mistakes. This is the flow process of the experimental setup. First, we set up the experiment like this, and then we attach the sensor, which is the accelerometer, which is also attached to the data acquisition, which is also attached to the laptop, and the output will be the analysis. Next is the signal processing, which is the process of improving the signal that have been obtained during the experiment to understand the signal even better. This includes noise removing, signal filtering, and other kind of processing. For processing the data obtained, MATLAB will be used to process the data by constructing a fast Fourier transform, FFT, and also time domain. Through MATLAB, any variables can be added or removed into the signal. Next is the signal analysis, which will be conducted after processing the data during the signal processing. From the signal obtained, the root mean square, RMS, standard deviation, skewness, and kurtosis will be calculated to compare the findings for both the normal and the bended shaft signal. Machine learning, such as classification learner, which is one of the apps in the MATLAB software, will be also used to verify the data obtained to confirm whether the data is valid or invalid. Next is the chapter 4, which is the result and discussion. When conducting the experiment on the vibration analysis of the normal and faulty shaft, standard ISO 7919 was followed. ISO 20816 was also used as a guideline for the measurement of vibration analysis signal. Here we have time domain and fast Fourier transform for normal shaft at 450 RPM. Here we have the time domain at 900 RPM and the FFT, which is also at 900 RPM. Time domain in FFT at 1350 RPM. And time domain in FFT at 1800 RPM. From the figure shown above just now, the finding shows that the difference of each vibration in terms of acceleration, amplitude, depending on its speed. The time domain increases in terms of acceleration due to the increase of RPM. This is also the same for the FFT, in which the amplitude increases because of the increasing of RPM. At 450 to 1800 RPM, we can see that the amplitude steadily drops and shows less movement in each of the data. Each of the data was recorded 3 times to avoid any errors and was processed using the MATLAB software. Next, we have time domain and fast Fourier transform for the bended shaft. Here we have the time domain in FFT at 450 RPM. Here is the domain and FFT for 900 RPM. Here is the domain and FFT for 1350 RPM. And lastly is the domain and FFT at 1800 RPM. So from here we can see that for bended shaft, the results shows more aggressively spike compared to the straight shaft. This is because uh, uh, when the speed is increased, the fault in the shaft releases a more uh, more aggressive vibration. This is because the condition of the bend shaft causes more vibration when the speed is increased. This will cause the amplitude and the acceleration to be higher than the straight shaft. So at 450 RPM, the amplitude keeps on increasing until the speed reaches 1800 RPM, where the high speed was reached. Next is the comparison between normal and bend shaft using RMS. So from this graph, we can see that the RMS for the bend shaft increases abruptly when the RPM increases, while the normal shaft RMS moves more smoothly. The blue one is the bended shaft and the orange one is the straight shaft. Next is the comparison of normal and bend shaft using standard deviation. Uh, the standard deviation is more or less the same as the RMS. From here we can see that the standard deviation for the normal shaft, which is the straight shaft, increases in a smooth manner while the bend shaft increases drastically. This shows that the standard deviation is affected by the condition of the shaft when the speed is increased. Next is the comparison for the normal and bend shaft using kurtosis. From here, we can see that the kurtosis for the normal shaft drop steadily, for indicating that the movement of the shaft is smooth. The bend shaft, on the other hand, increases abruptly at 900 RPM to 1800 RPM, which is due to the condition of the shaft, which affects the movement. Next is the comparison of normal and bend shaft using skewness. Uh, for uh, for the uh, for the bend shaft, uh, the at 900 RPM, the skewness of the bend shaft spikes up before decreasing. This shows that at 900 RPM, the vibration due to the condition is higher compared to the other speed. Next is the machine learning. This one is the prediction model for the fine tree, which uses RMS against kurtosis. This one is the prediction model for cubic SVM, and this one is the prediction model for weighted KNN, subspace KNN, and prediction model for fine KNN. So from the table above, we can see that KNN has a higher accuracy compared to the fine tree and cubic SVM. For the KNN, for all the KNN, all of the 24 data here was predicted to be precise as the original data obtained from the experiment. For the fine tree, 6 out of 24 data, fine tree, here, 6 out of 24 data, this one, and this tree, it was predicted to be different from the results obtained from the experiment. Uh, Based on the fine tree, at figure 900 RPM for normal shaft, the fine tree predicted the shaft to be bent when in fact it was straight, and is the same for the bend shaft at 1800 RPM, where the fine tree is predicted to be normal shaft. As for cubic SVM, 4 out of 24 data were predicted different to the original data. From the SVM figure at 1350 RPM for the normal shaft, the cubic SVM predicted the normal shaft to be bent, but based on previous research, the SVM should be more accurate when using a large set of data compared to KNN. However, due to my data use is only 24 sets, the KNN shows more accurate results compared to the others. And next is the conclusion and recommendation. So in conclusion, the purpose of this thesis is to investigate normal and faulty shaft using frequency-based technique and verify using machine learning software. Using vibration signal analysis, the condition of the shaft was able to be monitored for both the normal and bended shaft. The data obtained from the analysis of the FFT using MATLAB was valid and almost similar to the previous research online. The data was also calculated using RMS, kurtosis, skewness, and also standard deviation. From this method mentioned in the literature review in chapter 2, the difference of both normal and faulty shaft can be observed and identified and be compared between each other. Using one of the MATLAB apps, the classification learner, the data obtained was able to be analyzed using advanced method to identify whether the data is valid or not. Although for the data in this thesis is in a small set, it does not, however, affect the accuracy of the software. On the other hand, this setback can be seen as a future reference for other experiments. It is concluded that the proposed vibration signal and the statistical parameters used in this thesis is a success. In other words, the objective of this thesis, which is to conduct vibration signal on the shaft fault using frequency-based technique and verification by machine learning, has been achieved successfully. Lastly is the recommendation. There are some improvements that can be made for future research. The number of shafts should be increased so that there is more variation of data obtained and not just using two types of shaft. The sensors used for the research should be also be upgraded by using a more advanced sensor so that the data obtained will be more accurate. Also, the positioning of the sensor should also be improved so that the data should only focus on the fault of the shaft. Next is the sets of data should be improved by obtaining an even larger sets of data to get a more precise analysis. In addition, the research can also use a more advanced statistical analysis to analyze the data obtained so that it can provide an even more accurate details and information. Thank you. That's all from me. Goodbye.